Hello everyone, I'm Jo Ashbourne, the Director of the St Cross Centre for the History and Philosophy of Physics, and I'd like to warmly welcome you all to today's special event in association with Oxford's Department of Physics. We have nearly 3,000 people signed up to join us today from all around the world. So good morning, good afternoon, and good evening across the time zones. We're also delighted to welcome all the panelists, discussants, and our discussion panel moderator. Such an extraordinary group of physicists will give us some fascinating insights today on the greatest physics discoveries of the 20th century. Our moderator is Professor Brian Greene, a string theorist who's Professor of Mathematics and Physics at Columbia University, where he also serves as the Director of Columbia's Center for Theoretical Physics. Brian is also Chairman of the World Science Festival, which he co-founded in 2008, and he's written a number of best-selling popular science books too. But perhaps topping all that, Brian's highest accolade yet just might be that he's had a species of Australian spider that uses waves to hunt its prey named after him. So with that, I'll hand over to Brian, who will introduce our panelists and discussants. Thank you, Brian.
Thank you, Jo. It's a great honor to be part of this program. Thank you and your colleagues for putting it together. And I think, as everybody knows who signed up, the focus today is on the tremendous breakthroughs in physics that occurred during the 20th century and continued onward into the 21st century. And think back to the early years of the 20th century, or just before the 20th century, there were serious, well-respected physicists at that time who doubted the existence of atoms, right? The notion, perhaps, of black holes, the term hadn't even been coined, and yet today we've got images of black holes. Today we can manipulate the microscopic realm with fantastic precision. And the 4 Nobel Prize winners that we have here today have played a vital role in pushing the frontier of understanding forward. And it is thrilling to have them all together in one place to give us their insights into how our understanding of the universe has changed, progressed, developed over the last 100 years. So I'll introduce each of the speakers when their turn to speak comes, but just so everybody knows what we have in store, it's Professor Stephen Weinberg, Bill Phillips, Tony Leggett, and John Mather. We also have a group of discussants who, after the presentations, will lead a question session with the Nobel Prize panel, and they include Professors Jocelyn, Burnell, Jim Gates, and Chung-Pei Ma. Those of you who joined us right at the start at 12 o'clock were also treated to an impromptu Nobel Prize comedy moment, and I just want to note that that was led by Bill Phillips and Tony Leggett, for whom we are quite thankful for the levity that they brought to today's proceedings. All right, so let's begin with our first speaker. Professor Stephen Weinberg holds the Josie Regental Chair in Science at the University of Texas at Austin and won the Nobel Prize in Physics in 1979 with Abdus Salam and Sheldon Glashow for his contribution to the theory of the unified weak and electromagnetic interaction between elementary particles, including as well the prediction of the weak neutral current. I will also say, from a more personal perspective, Professor Weinberg's books, both popular books and textbooks, for me personally, played a profound role in my own interest, enthusiasm, and education in physics, for which I will be eternally grateful. And his willingness to reach out to the public certainly inspired a similar interest that I myself have pursued during my career. So with that, let me turn over the microphone and the floor to Professor Stephen Weinberg.
Well, I gave the best part of my talk already, but we're supposed to offer opinions about what are the greatest physics discoveries of the 20th century. And if by a great discovery you mean one that was essential for future progress, then there are a lot of them, and they're hard to compare. For example, in 1911, Lord Rutherford recognized that the atom consists of a tiny nucleus which contains almost all the mass, around which electrons circulate in orbit, held in orbit by electric attraction. Without that discovery, all future progress in atomic or molecular or nuclear physics would have been impossible. What could be greater than that? So I'm going to narrow down the definition of great to mean a discovery that not only changed what we say about nature, but changed the very language in which we talk about nature, that changed the way we are able to think about nature. And in that respect, I think quantum mechanics is clearly the greatest discovery of the 20th century because it changed the conceptual foundation from which we view nature. In the mechanics that preceded it, in classical mechanics, you describe the state of a system by saying where every bit of matter is at every moment and how fast it's moving. Quantum mechanics is entirely different. The state of a system is described by specifying a vector. That is a quantity that, an arrow that has a definite direction and a definite length, not in 3 dimensions, but in a space of infinite dimensionality called Hilbert space. Each state is represented by a different kind of vector. For example, for a system consisting of a single particle, like an electron and a hydrogen atom, there is one different vector for every possible position of the electron. But those aren't the only kinds of vectors. You could have, for example, 2 vectors that represent 2 possible positions of an electron and form another vector by adding them. Now, when you do that, you don't get a vector representing a state where the electron is at some intermediate position. You get a vector representing a state in which the electron doesn't have a definite position at all. And indeed, since an electron can take any one of an infinite number of positions, you can add up vectors representing states with all those positions and get a vector in which the position is entirely indeterminate, but in which the state has a definite velocity. Indeed, as Heisenberg recognized in his uncertainty principle, the more definite the position, the less definite the velocity, and vice versa. You can go beyond this, and as Schrödinger pointed out, in principle at least, you can imagine having a vector representing a state in which a cat is alive, and another vector representing a state in which a cat is dead. And when you add them, you don't get a vector in which the cat is having a nice nap. You get a vector representing a state in which the cat is not necessarily alive nor dead. It's more like adding musical notes. When you add 2 musical notes with different frequencies, you don't get another note with an intermediate frequency. You get a chord, which has its own sound, a distinctive sound. Well, curiouser and curiouser, as someone said, but it gets worse. In quantum mechanics, quantities that represent observables, vectors that represent, quantities that are observable, like energy or momentum or position or spin, are represented by operators, that is, by operations on these vectors that may cause the vector to change its direction or change its length. And I'm not in this, as I usually would, trying to make quantum mechanics seem relatively accessible and familiar. I'm trying to emphasize how strange it is, and indeed how strange it must have seemed to the physicists in the first decades of the 20th century to underline how really great a discovery was, how great a break with the past it was. Now, everything I've said so far is just vectors and operators. It's just mathematics. In order to give some physical meaning to this, you have to add interpretive postulates. And the first interpretive postulate is that if you have a state represented by a particular vector and an observable represented by an operator on vectors, and if that operator doesn't change the direction of that vector, but just changes its length by some numerical factor, then that state represented by that vector is a state in which that observable has a definite value. For instance, there's an operator called the Hamiltonian, which represents the energy of a system. If the Hamiltonian operator acting on the vector representing a state doesn't change the direction of the state, then that state has a definite energy, and the energy is equal to the numerical factor by which the operator changes the length of the vector. That vector, like any vector, can be represented as a sum of the infinite numbers of vectors representing states in which the electrons have definite positions. And the lengths of the individual vectors in that sum, of course, depend on the position represented by those individual vectors. And put together, they form what's called the wave function of the state. The wave function is the functional relation between the length of the vector representing a given position as it appears in the sum of vectors for the vector that represents the state of the system. It was Schrödinger in 1926 who first wrote down the rules for finding the wave functions of states of definite energies. And he found, solving these rules represented by a differential equation, that in order to get a sensible wave function, one that wasn't discontinuous or infinite somewhere, there are only certain allowed energies. These were the allowed energies of the atom or molecule or whatever that he was considering. And he recognized that, as indeed Bohr had anticipated, that these allowed energies accounted for a phenomenon that had mystified physicists since the beginning of the 19th century. But when you look at the spectrum of an atom, you see it crossed. For example, when you look at the spectrum of a star or a flame, you see the rainbow crossed by dark or bright lines. And these dark or bright lines are the energies of light emitted when an atom or molecule or whatever it is makes a transition from one of Schrödinger's allowed energy states to another one of them. So that Schrödinger was justly proud that he had explained atomic spectra in terms of solving an equation for the wave function of the electron. Well, quantum mechanics went on from greater to greater and greater successes. But there's more to it than that. And so far, with what I've said about observables having definite values, although it must have been terribly strange, I don't think it raised any particular philosophical problems. The problems arose with the next postulate, which has to do with probabilities. If you have a state represented by a vector, and you measure an observable, and this state is not a state that has a definite value for that observable. In other words, the operator representing the observable doesn't leave its direction unchanged, but swivels it around. Then that state is not a state in which that observable has a definite value, as I've already said. but you can write it as a sum of states in which the observable has definite values. It might be a position. I've already talked about that. And if you measure the observable, the probability that you will get any given value for that observable is equal to the length of the corresponding vector in that sum. This is, for example, when you're talking about positions, the probability when you're in one of Schrodinger's states of definite energy that you will get, if you measure the position of the electron, that you'll find a definite position, is given by the length of the vector representing that position in the expression of the vector representing the state as a sum of all vectors representing definite positions. In other words, it's proportional to the magnitude of the wave function, actually the square of the magnitude of the wave function. That's a rule that's known as the Born rule because it was first recognized by Max Born, who was in 1926 or 27. He was the first to recognize the probabilistic nature of quantum mechanics. This appalled many physicists at the time, including Einstein, who with his collaborators in the 1930s pointed out all kinds of really counterintuitive consequences of the introduction of probabilities into the rules of physics. I think, like most of us, I've felt that now that this is just something we have to live with. This is the way the world is. I mean, where is it written that the laws of nature have to be deterministic? And I approve of the advice, the legendary advice that's generally given to graduate students who worry too much about the probabilistic nature of quantum mechanics. The advice is shut up and calculate. And indeed, the calculations that we do in quantum mechanics have been unbelievably successful, not only in accounting for the spectra of atoms, as Schrödinger did, but in accounting for the properties, all kinds of properties of atoms and molecules, atomic nuclei, and indeed of all matter. I think one of the greatest successes of quantum mechanics has been in the direction of reductionism. At the beginning of the 20th century, there were physicists like Millikan who thought that physics was just about at the end of its work. All that was needed was to measure a few more constants to a few more decimal places. I don't think that represented hubris on their part. I think it represented a limited view of the capabilities of physics, because they could not, at the beginning of the 20th century, have thought that quantum mechanics had already explained the principles of chemistry. Rather, they just didn't think that was the job of physics. Chemistry was a separate science. The chemist down the hall would worry about that. The physicist would do his job. There would be no relation between them. But that, in fact, is what has been what's happened. The principles of chemistry have been, by and large, explained on the basis of quantum mechanics. And we now see nature in a far more unified way than would ever have been possible before. Indeed, the progress that we've made in understanding nature at the deepest level to which we have so far reached, the standard model of elementary particles, has been entirely based on the quantum mechanics that was already in its mature form at the end of the 1920s. Well, despite the triumphalist note of these remarks, I have to say that in recent years, I've had some second thoughts. Not about whether we're right in using quantum mechanics, of course we are, but whether quantum mechanics will survive forever in precisely its present form. My problem doesn't have to do with probabilities. We can live with that, but with observers. It bothers me very much that no one has found a way of stating the postulates of quantum mechanics without bringing the existence of observers into the postulates. Now, of course, every science has to tell you in the end what an observer will find, because that's the way we test our scientific theories. That's what it's all about. But as a consequence of the postulates, not as part of the postulates themselves. For example, in Newtonian mechanics, if you make assumptions about the solar system and the existence of beings with minds and eyes, and the fact that light travels in straight lines, you can deduce what observers will observe when they look at the sky. You don't put the observers into the Newtonian laws of motion, but that's what we seem to be forced to do in quantum mechanics. So quantum mechanics, in a way, represents a retreat from the old aim that physics or science would account for everything, not just atoms and planets, but observers as well. And so I'm not so sure that quantum mechanics will survive as anything but an extraordinarily good approximation in the centuries to come. And some of us have begun to think about looking for ways of looking for tiny departures from quantum mechanics. For example, the extreme precision of atomic clocks shows that one particular kind of departure from quantum mechanics does not contribute as much as 10 to the minus 18 electron volts, roughly 1 part in 10 to the 18th, to the energy of the atoms used in these atomic clocks. No departure from quantum mechanics as a lot has so far showed up. So, alas, we are stuck with a theory which works extraordinarily well, but whose foundations continue to puzzle us, and which may not survive in precisely its present form indefinitely into the future. Thank you.
Thank you very much, Steve. That was a wonderful talk, and we're going to have a discussion section at the end, but I can't help but ask one quick question right now. So the point that you make about quantum mechanics and the awkwardness of having to introduce observers right into the formalism, oftentimes people describe this in terms of the quantum measurement problem. You know, how do we transition from the probabilistic haze of the mathematics that you so adeptly described to the definite reality that we find when we observe or we take a measurement? There is an approach to quantum mechanics called the de Broglie-Bohm approach, which at least in principle offers a way of addressing the quantum measurement problem. It has other issues too, but I'm wondering, is that an approach that resonates with you at all, or do you not think that's the right direction to go?
Well, that's a big question. I have to say there are a number of different schools of thought, each one of which has solved the quantum measurement problem, but the solutions are all different, which makes one wonder. The de Broglie-Bohm approach is one of them, and I have continually been challenged by its advocates. I don't think it solves the problem at all. The observers sneak into its postulates, although not in precisely the same way as they do in conventional quantum mechanics. So I don't think it solves the problem.
Great, thank you.
But I'd be happy if it did.
Yeah, I think many of us would be as well. Okay, so we'll come back to questions in that domain when we get to our discussion section, but now let's move on to our second speaker for today, which is Professor William Phillips, who is a professor of physics at the University of Maryland, College Park, and works at the National Institute of Standards and Technology. He shared the Nobel Prize in Physics in 1997 for the development of methods to cool and trap atoms with laser light. And again, I'll also note that Professor Phillips, also Professor Weinberg, both have participated in the World Science Festival. And Bill Phillips gave a legendary talk that people still talk about. I think it was called Einstein, Time, and Cool Stuff. So it's really an honor to welcome him to this afternoon's discussion. So the floor is yours, Bill.
Thank you very much, Brian. And I hope that you'll interrupt me if my audio or my video is not what it should be. I'm hoping that right now you're seeing my first slide, which says my pick for the greatest physics discovery of the 20th century. Is that?
We are seeing that.
Excellent. It's not perfect, but as far as the slide, but my choice is the same as Steve Weinberg's, and I'm going to try to present it from a somewhat different perspective. But when I thought about the various things that had gone on in the 20th century, and there was an amazing set of discoveries, I couldn't avoid choosing quantum mechanics, and you'll see why shortly. But one of the reasons is that I'm from a place called the Joint Quantum Institute. And when quantum is your middle name, what other choice do you have? Okay, why quantum mechanics? Or another way of stating that might be, why do I love quantum mechanics so much? Well, as Steve pointed out, quantum mechanics represents a really fundamental change to the way we think about physics. It has changed our worldview of physics in a way that is more profound, for example, than Einstein's theory of special relativity. It changes our very notion of what constitutes reality. And maybe Tony Leggett will talk a little bit more about that later, but that, I think, goes even beyond our worldview of physics. As Steve pointed out, quantum mechanics is incredibly successful. What it calculates things to incredible accuracy, confirmed by experiment, but at the same time, quantum mechanics is deeply weird. In fact, it is so strange that Richard Feynman, one of the iconic physicists of the 20th century, said that nobody understands quantum mechanics, and if you aren't bothered by quantum mechanics, then you simply haven't thought about it carefully enough. And that is deeply appealing to me, that weirdness of quantum mechanics. And while it works so well, this essentially perfect theory, it leaves a lot of fundamental questions unanswered. The ones that Steve brought up, but some others that I'm going to bring up myself. And another thing, the final thing that I like about it so much, the next to the final thing that I like about it so much is that it has changed our lives. Not just the lives of physicists who have to think about the physical world using the laws of quantum mechanics, but the lives of everyone. The technology that has sprung from our understanding of quantum mechanics has changed the lives of almost everyone on the earth. And finally, in the 21st century, we're in the midst of a new kind of revolution, a technological revolution that uses some of the weirdest aspects of quantum mechanics. And I find that wonderfully appealing. So here at the top is a, let's see now, I'm not doing a very good job of okay, that was what I just talked about. Here at the top of the page is a picture of the first transistor. It wouldn't have been possible to have invented the transistor if people hadn't been thinking about the motion of electrons in semiconductors in a quantum mechanical way. And that invention of the transistor, which was around 1947 or 48, led to a tremendous bloom of practical applications in semiconductor electronics. Here's a picture of an integrated circuit, a computer, much like the one I'm giving this talk with, cell phones, we all have them in our pockets or in our holsters, even people in the most remote areas of the world often have cell phones. And the only reason these things exist is because we have understood quantum mechanics. In the absence of that, we never would have been able to make all of these amazing technological wonders. Now, here, I want to bring up a technological application of quantum mechanics that is very personal for me. These three people right here. This is Dan Kleppner. He was my thesis advisor. This is Norman Ramsey. He was Dan Kleppner's thesis advisor. And this is I. Robbie. He was Norman Ramsey's thesis advisor. Now, Robbie came up with the idea of an atomic clock, using, in a sense, the ticking of atoms as the ticker for a clock. It was Ramsey who came up with the key idea that almost all atomic clocks are based on, and who made some of the first atomic clocks. And Dan Kleppner made what was at the time invented and made the hydrogen maser, which was the best clock at the moment. And clocks like these are in satellites, a constellation of satellites that orbits the Earth, that provides the heart of what we call the global positioning system, the GPS, or the satellite navigation system. And here's a picture of one of those satellite navigation receivers that one often has in one's car. And using this thing, you can navigate your way across continents, and you can navigate your way to an unfamiliar address in your own neighborhood. So that kind of practical application has made quantum mechanics a fundamental part of everyone's life, even if they don't realize it. Now, what is it that quantum mechanics did that fundamentally changed our view of physics? Well, I'm going to take a slightly different view than the one that Steve Weinberg took, and say that, at least in some sense, what quantum mechanics gave us is wave-particle duality. What does that mean? What it means is that everything in our experience is both a particle and a wave at the same time. So things like electrons and atoms that we are used to thinking about as if they are particles have a wave character. And things like light and sound that we are used to thinking of as being wave phenomena also have a particle character. And this central equation here, that the lambda, the wavelength, is equal to Planck's constant divided by the momentum, applies to both kinds of things. This was the relationship that Louis de Broglie came up with in around 1923. And what it tells us is that if we have a particle and we know what its momentum is, its mass times its velocity, then dividing that momentum into Planck's constant will give us the wavelength. On the other hand, if we have some wave phenomena and we know the wavelength of that wave phenomena, all we have to do is plug it into this equation. It will tell us the momentum of the particle that is associated with this wave. Now, often you hear people say that quantum mechanics is a theory that describes the microscopic world. And that's sort of true. And here's why. If you ask what is the wavelength of some ordinary object, like a billiard ball, because Planck's constant is so small, and the momentum of the billiard ball is typically quite modest, but still, fairly large, then what it means is that the wavelength is incredibly small, because this number is incredibly small, this number is modest, and you end up with a wavelength which is almost unimaginably tiny, about 10 to the minus 30 meters. Now, 10 to the minus 15 meters is the size of an atomic nucleus. So 10 to the minus 30 is smaller than an atomic nucleus is than a meter stick by that same proportion. So this is just ridiculously small. Smaller, way smaller than the atoms that are in the billiard ball. It is so small that it simply doesn't matter. By contrast, if you think about the electrons that are going around an atom in the model that Rutherford came up with, as Steve Weinberg mentioned, the wavelength turns out to be about 10 to the minus 10 meters, and that's the size of the atom itself. So when the wavelength becomes equal to the size of the object that that we're talking about, you'd better pay attention to the wavelength, and that happens at the microscopic level. So let's talk a little bit more about atoms. Now, Steve Weinberg reminded us that at the beginning of the 20th century, a lot of people didn't even believe in atoms. In fact, it was Einstein's theory of Brownian motion that convinced the majority of people that atoms existed. Now, Steve also mentioned that there were a lot of phenomena that people didn't understand in the 19th century, but that they didn't really recognize as being something that was the province of physics. And that's absolutely right. They are the province of physics, and they weren't understood. And the reason they weren't understood was because we didn't yet have quantum mechanics. Now, here's a sort of example of that. You've heard about Rutherford. He came up with this model of the atom with electrons going around a nucleus. Now, I want to emphasize that while this picture of an atom is still the one that we recognize as being the iconic picture of the atom, it is completely wrong. And nevertheless, we still sort of carry it in our minds. But it was 1911 that Rutherford came up with this picture of the atom based upon his measurements that he'd made just a few years before, shooting alpha particles into a gold foil, and came to the conclusion that atoms had to look like this. But Rutherford was reluctant to put forth this theory of what an atom had to look like, because he realized that this atom could not exist. If the atom really was electrons going around a nucleus, then those electrons would radiate light, lose energy, and the electrons would fall into the nucleus, and this atom wouldn't exist. And that means we wouldn't exist, and nothing else in the world that we experience would exist. And Rutherford understood that, but he understood that his experiments showed that this was pretty much what an atom looked like. It took Bohr a couple of years later to apply quantum mechanics to this idea, the very beginnings of the ideas of quantum mechanics, to show how the atom would be stable. But more than that, to show that the light coming from the atom that Weinberg mentioned, the spectrum of the light coming from such an atom, was explained by his simple model. More than a decade later, Schrödinger and Heisenberg came up with a much more sophisticated theory, had a picture of an atom that looks a little bit more like this, where this represents something like the probability distribution of where the electron is. And that is the kind of image we ought to carry around for atoms, but we're still stuck on the old Bohr-Rutherford model. Now, so quantum mechanics explained all kinds of things that either weren't explained in the 19th century or weren't even recognized as being something that ought to be explained in the 19th century. And quantum mechanics explained so much of it. Essentially explains everything that it can calculate. And it does this with an underlying weirdness that I want to emphasize along with what Steve Weinberg said. The uncertainty principle is one of the things that has been mentioned, the idea that you cannot simultaneously know where something is and what its momentum is or what its velocity is, and that the product of the uncertainties in those two physical quantities always has to be bigger than something related to Planck's constant. Remember, Planck's constant is really small, so this doesn't come up until we're at the submicroscopic level typically. But it also means that if you've got any object and you want to measure its momentum or you want to measure its position, there's no way of predicting beforehand what those numbers are going to be. This disturbed Einstein so much that he said, I cannot believe that God plays at dice with the universe. In other words, that the result of a measurement is going to be random in a fundamental way, that somehow it should be like in classical physics, where lots of times we don't know what the result of a measurement is going to be. Imagine flipping a coin, for example. We don't know whether it's going to come up heads or tails. That's why we flip it. But we believe that if we could just make measurements carefully enough, we could predict whether it landed heads or tails. We also believe that once it lands, even if we don't look at it, that it is either heads or tails. But quantum mechanics tells us something different. Quantum mechanics tells us that if we had a quantum coin, like an electron, and we flip it, which is to say we do something to it to alter the direction in which the magnetic moment of the electron is pointing, so that it ends up in a superposition of pointing in one direction and pointing in the other direction, that unlike the coin, it's not as if it's pointing in one direction or the other and we simply don't yet know it, but will once we measure it. No, quantum mechanics tells us something very different. Quantum mechanics tells us that the state of that coin, that quantum coin, the state of that electron, does not even exist until we measure it. And this has been what Brian Greene referred to as the quantum measurement problem. How do we go from this state, which is very well described in quantum mechanics as being a superposition of being in two possible states or many possible states, to the case where when we measure it, it becomes just one of those things? How does that happen? And as Steve Weinberg pointed out, lots of people have come up with lots of explanation. I'm in the camp that he described as shut up and calculate, because all these different explanations don't change a thing about what we predict will happen when we actually make measurements in the laboratory. And to me, if it doesn't change what I'm going to observe, then it's not physics, it's philosophy. And no one has yet come up with a testable theory for how this works that will predict something different than what standard quantum mechanics does. There's a lot of work going on about it at the moment. When I say testable, I mean with an experiment that we can do right now. There are hypotheses that maybe we'll get better at testing as we improve our techniques, but for the moment, nobody has an interpretation of quantum mechanics that can be distinguished from another interpretation of quantum mechanics by actually making measurements. Now, I just want to talk a little bit about superposition. How is it possible for something to be heads and tails at the same time? That just seems to be too weird. Look at this picture of a cube. Now, I think that you've all seen pictures like this, and what you realize is that depending upon how your mind conceives of this picture, it could look like this, or it could look like that. And as you look at this picture of the cube, you can make your mind pop it back from one or the other. So in a certain sense, this is an illustration of how something can be in two states at the same time. Before you look at it, you don't know which way this cube is pointing, but when you look at it, your brain, in a sense, makes it be this or that. And I want to emphasize that this is a pale analogy to what quantum mechanics really is like. There is no good classical, which is to say non-quantum analog to this idea of superposition. But this weirdness has enabled quantum mechanics to be absolutely amazing in its ability to predict physical phenomena. The electron G factor, a kind of a measure of how strong the magnetism of an electron is, can be calculated in quantum mechanics. And here's the number. There's a little bit of uncertainty in that calculation. Don't want to go into the details of why that is, but this is calculated to better than a part in 10 to the 12. There is no other physical quantity that we either know or can calculate to this level. And it's measured to a similar precision, and it's right. And to get this calculation, you have to understand all sorts of other weird stuff. For example, you have to understand that the vacuum is not empty. The vacuum is full of virtual particles that are popping in and out of existence, and those things go into this number, and it's something that we can confirm experimentally, that these weird features of quantum mechanics, like the fact that the vacuum is not empty, are in fact correct. So quantum mechanics essentially perfectly calculates everything that we can calculate. The standard model, which is a kind of extension of quantum mechanics, something that Steve Weinberg had a lot to do with, and that Brian Greene is trying to go beyond. It explains everything except for what it doesn't explain. So what is left that it doesn't explain? Well, one of the things is gravity. One of the great challenges of physics today is to unify the theory of quantum mechanics with the theory of gravity in the way that Steve Weinberg and his colleagues unified the theory of electromagnetism and the theory of the weak force. This unification has been incredibly resistant, and we don't really know how we're going to unify it. Most people feel confident that we will, but some people aren't even sure that we will. We don't know why we exist. There ought to be a nearly equal amount of matter and antimatter in the universe, and there isn't. The universe is mostly what we call matter, and as a result, we exist. If that wasn't true, it all would have annihilated with each other at the beginning of the universe, and we wouldn't be here. We know that only about 5% of the entire mass energy of the universe is made up of atoms and electrons and protons that we understand about. The rest of it is made up of dark matter and dark energy. 95% of the universe is made up of stuff that we have no idea whatsoever what it is. And my feeling about that is, what could be better than that? To live in a world where 95% of what the universe is made of is not understood in the least. What a wonderful situation to be in, to have that much more to learn. And from a practical point of view, we are in the midst of what some of us have called a second quantum revolution, a technology that uses the weirdest parts of quantum mechanics. You see, all these weird things that I told you about quantum mechanics, people understood in the 20th century, but the technology of the 20th century didn't use those weird parts of quantum mechanics. And now we're starting to develop technology that does use those weird parts. This is really going to be fun. Thanks very much.
Thank you, Bill, for that inspiring talk. And again, just a quick question before we move on. You mentioned that Einstein said that he couldn't believe that God played dice. And of course, Niels Bohr responded by saying Einstein stopped telling God what to do, which seems to resonate with the perspective that you have. We just need to accept that this is how the world works. But my question is this. You mentioned that from your perspective, you're just not that interested in these various approaches to quantum mechanics because they don't change the predictions, the kinds of things that you would go out and measure. But what do you say to people like me who would put forward the possibility that physics isn't just about making predictions? Physics is about telling the most precise narrative of what's actually happening, how reality actually works. And each of these different approaches to quantum mechanics does tell a different story, does give a different narrative. Why doesn't that fire you up?
Well, okay, first of all, to be honest, it does. I am, in fact, interested in these interpretations of quantum mechanics, but I have to be honest and say that if we've got multiple interpretations of quantum mechanics, all of which predict the same thing, then that means these are not really alternatives. They can't be a description of what, quote, really happens, because we have all these different things and they predict the same things. So they're really just a kind of way of making your discomfort be a little bit less, and then you get to choose which way you want to feel comfortable, but you have no way of saying that your way of feeling comfortable is better than somebody else's way of feeling comfortable until you make a prediction that could experimentally be different from what somebody else predicts. So for example, I have a friend, many of you know Arthur Eckert, and he loves the many worlds interpretation of quantum mechanics. The idea that says when you make a measurement, it's just your world where you get the result that you do. And there are an infinite number of other worlds where different results have happened. And he promised me that with an hour and a bottle of wine that he could convince me of the correctness of the many worlds interpretation of quantum mechanics. I'm pretty sure that that ability to convince me would have a lot more to do with the quality of the wine than it would have to do with the quality of the hour that he would spend expounding the virtues of the many worlds. But I'm really excited about people who predict observable differences, the idea that there might be something what we call a fundamental source of decoherence, something that in nature causes this superposition state to go one way or the other, even if we don't measure it. And people have suggested that, and so far, no experiments have succeeded in seeing that. But that is something that I do like, because I'm an experimentalist. I want to measure stuff. And after all, let's face it, one of the definitions of what distinguishes science from other things is that it's about things we can measure.
Absolutely. So thank you very much. Let's move on to the third speaker, Professor Sir Anthony Leggett, who currently serves as the chief scientist at the Institute for Condensed Matter Theory at the University of Illinois at Urbana-Champaign. He shared the Nobel Prize in Physics in 2003 for pioneering contributions to the theory of superconductors and superfluids. Anthony, the floor is yours.
Thank you. What I'm going to be talking about is actually fairly closely connected with what Steve Weinberg and Bill Phillips have talked about, but I'll try to emphasize a little more the consequences, the ultimate consequences of the way in which we think about the everyday world, rather than the world of atoms and electrons and so forth. So that's what I want to talk about. As I say, it doesn't look at first sight like a very remarkable sentence. I imagine can be translated into most languages without any problem, can be say it could be right or it could be wrong, etc., etc. It's a very everyday feature of our everyday life. So what I actually start from is a thought experiment which was actually proposed. See this one too? Okay. So, so this experiment was actually proposed way back in, I think, 1936 by Einstein, Podolsky, and Rosen. And as I'll explain in a moment, about 30 years later, in 1964, the late John Bell made a very important discussion based on it. So this is how the experiment goes, basically. You start off with an atomic source which emits two objects in opposite directions. They're actually photons, but we don't necessarily have to know that. And these two objects then travel a very long distance to two different measuring stations. In some recent experiments, the distances involved have been of the order of 1,000 kilometers. And these two stations, I mean, they can be purely automated, but we can imagine that they're run by two characters who in the literature are traditionally called Alice at this station and Bob at this station. And what Alice, say, at station number 1 does is she activates a random switch which will switch any particular photon into one of two measuring devices. The important thing to realize is that these two measuring devices measure different things, so that you cannot measure both of these things on any one photon. You've got to decide, or the random switch has got to decide whether to switch that particular photon into measuring apparatus A or measuring apparatus A prime. As some similar things go on at the other end of the laboratory, which, remember, in this case could be 1,000 kilometers away, so it's a very, very long distance away. Now, let's just discuss for a moment what these measuring devices consist of. We're actually going to measure in practice the polarization of a photon. So what we do is to first put it through something called a polarizer, which is set up in such a way that it will transmit a photon whose axis is, let's say, in the vertical direction, and it will reflect a photon whose axis is, polarization axis is out of the screen. Well, so far so good, but of course we want to actually know that whether it has been transmitted or reflected. So we set up here some kind of measuring device, typically a photomultiplier, which will, so the photon will enter that photomultiplier if it gets through the polarizer, and it will start a cascade of electrons that will then trigger some electronics. And at the end of the day, there will be certain kinds of everyday level events. We get a bell to ring, we get a light to flash, we get a computer tape to be printed out. So in that case, if that happens with a particular photon, we say by definition that photon has a value of the variable A, which is +1. Yes, it did have +1. If, on the other hand, the photon is reflected from the polarizer, it'll go into a different counter, the no counter, and again, electronics will be triggered, etc., etc. And we then say that the value of A is -1. So we have a perfectly everyday level macroscopic event which tells us whether the photon had the value A equals +1 or A equals -1. But remember that if we did that, we couldn't simultaneously switch our photon into counter A prime. Now, we can define a kind of theory which we'll call an objective local theory, and it actually turns out that what's actually measured here directly, what's measured is the correlations. That is, we count the number of times in which photon number 1 is switched into counter A, and A gives +1, say, and a photon of the same pair was switched into counter B and gave +1, say. So we multiply those together, and that gives us a contribution to the correlation of A and B, which is +1. If, on the other hand, B had given -1, then the contribution would be -1. We only do that, of course, for those photons which number 1 was switched into A, and number 2 was switched into B. There's another set of photons for which 1 was switched into A, and 2 was switched into B prime. And for that set of photons, we can again work out the contribution to the correlation of A prime times B, etc., etc. So the raw data can be regarded as these correlations. Now, it's a rather straightforward argument, in retrospect at least, which tells you, this is basically the argument that John Bell gave in 1964. It's a rather simple argument which tells you that this combination of correlations has to be less than or equal to 2. Now, had anyone bothered to work that out in, say, 1900, way ahead of quantum mechanics, and suggested to go that we should just test this and experiment, I think his colleagues would have said, well, there's no point. It's just so obviously true. We'll see why it looks so obviously true in a moment when we actually discuss what objective local theories are. But what John Bell showed in 1964 was that this inequality, which looks so innocent and harmless, is actually violated by the predictions of quantum mechanics. Well, of course, the story doesn't stop there. People were very eager to find out what experiments said about it. And over the last 40 or 50 years, there have been or hundreds and hundreds, I would say by now, of experiments on this, crudely speaking, on this experimental setup. And what they show is that very definitely this combination of quantities is greater than 2, and greater than 2 by an enormous number of standard deviations. So the experimental data then do violate this, and therefore show that any theories which have the objective local quality, and we'll just come to those on the next slide, they cannot be valid. Next slide, please. Next slide, please. Thank you. Okay, so the question is, what do the idealized Bell, EPR Bell experiments show? So basically, objective local theories are theories which embody the conjunction of 3, or some people like to say 2, different postulates. The first is that that of reality. Crudely speaking, physical systems have properties independently of whether or not they're observed. The second is locality, or sometimes called Einstein locality. No causal influence can propagate with a velocity greater than the speed of light. And the third is the absence of retrocausality, that future events cannot affect present or past events. In other words, ensembles, that is the collection of systems to which we apply our physical description, are characterized only by the initial conditions, their preparation and so forth. Crudely speaking, the arrow of time runs in only one direction. Just as a short note, in special relativity, 2 can actually be shown to imply 3, but there could be, we can think about more general theories of the world in which that didn't happen. So one of these principles then has to be wrong. Which is it? Well, if we challenge retrocausality, then I think we're really in rather serious trouble, because we really don't even know how to set up an experiment in a meaningful way if all sorts of causal effects are going to suddenly come in from the future and complicate things for us. Locality. Well, it is possible to sacrifice locality, and there are physicists who prefer to draw this conclusion from the results of these EPR Bell experiments, but I think it's probably fair to say that on the whole they're a minority. So, and the reason for that, crudely speaking, is that locality is a very, very fundamental part of Einstein's theory of special relativity, which is probably the best verified theory in the whole of physics. So we really don't want to pull that away and let the whole edifice of special relativity crumble. So the only final choice then is to challenge or sacrifice the idea of realism or objectivity. Let's just try to discuss that a little more. And this ties up, I think, rather closely with some of the things that both Steve and Bill talked about, but let's say a little more about it. Imagine then that we, for a moment, think about a single photon. It's heralded, that is, we know it's coming. And we've actually got a switch here, which will switch us either into a measuring device, same as we had previously, or into somewhere else, which we'll just call elsewhere. So imagine that a single, particular photon is directed elsewhere. Then what does it actually mean to ask, does it have, imagine that this measuring device was supposed to measure the quantity A, as in the earlier diagram. What does it mean to ask, does it have a definite value of A? Well, here is a possible quasi-operational definition, and this is an idea which has been developed by a number of people, in particular by Henry Stapp and the later Asher Perez, but others as well. And it goes something like this. Suppose that the photon had in fact been switched into the measuring device. Then we can basically think about two statements. And again, I don't think this is a quirk of the English language. Again, I encourage you, if your native language happens not to be English, translate it into your native language and see if it makes sense. I think it will. So, proposition 1 is the statement that it is a fact that either counter y would have clicked, that is a equals plus 1, or counter n would have clicked, that is a equals minus 1. Seems rather difficult to doubt that, because every time that we actually do switch our photon into this counter, one of those two things happens. So that looks pretty much like a truism. Anyway, so so this second sentence, either it is a fact that counter y would have clicked, or it is a fact that counter n would have clicked. That is the statement of so-called macroscopic counterfactual definiteness. And in some sense, people who like Stapp and Perez and so forth believe that this is essentially what we mean, or what we could mean, by realism. And this is rather nicely encapsulated in a little paper by Asher Perez, which simply has the title, "Unperformed Experiments Have No Results." Well, so far, so good. But how do we, one slight problem with this, and one slight problem, in fact, with the interpretation of the EPR-Bell experiments. We're basically assuming that something happened at some point during the measuring process. For example, a definite outcome was realized when this particular photon, which was switched into the counter, actually passed or failed to pass the polarizer. But now, wait a moment, we know that can't be right. Quantum mechanics predicts, and we can actually demonstrate experimentally, it is not the case that each individual photon would definitely either transmitted or reflected. There are cases in which we can show that both of those possibilities must still exist at this stage. Well, maybe then when the photon would have gone into the photomultiplier and triggered a big shower of electrons, did something happen then? Again, quantum mechanics says no. And although we can't demonstrate it right now by experiment, I think most people believe that, in principle at least, that is also true. And so on and so forth. So at the end of the day, it really isn't clear not only when a definite outcome was realized, but even if a definite outcome was ever realized. Now, when I put this to my experimental colleagues, I don't know if Bill will agree with this, most of them say, well, no, look, we really know that something happened when, say, the counter went into the photon went into the counter, and we got a click, or didn't get a click, or light flashed or something like that. Do you? Do you actually know that? Until you've actually looked at it? Well, let's think about that for a moment. This is basically a question related to the Schrödinger's cat paradox, which Steve mentioned briefly. It's about whether quantum mechanics allows definite outcomes ever to be realized. Well, okay, let's try to approach this from a slightly different angle. Let's try to see whether there are cases whether we can actually examine whether things that happen at the level or close to the level of everyday life actually happen or don't happen. How do we do that? Well, what we actually have to do is to go to a rather different kind of experiment. This kind of experiment is perhaps not quite so well known as the as the EPR belt experiments, but it's one in which I have myself been quite involved. So could we have the next slide, please? Okay, no, yeah, good. Okay, so for this experiment, we need a system which is reasonably macroscopic, that is at the level of everyday life, which has available to it two states which by some reasonable criterion we can say are macroscopically distinct. The example which is actually used in the experiment is a superconducting ring interrupted by a Josephson junction. And the two states that we're going to be talking about are states corresponding to a current flowing either anticlockwise as here or clockwise as here. This Q equals -1. Crudely speaking, what we would like to do is to see whether one of those two states, which are reasonably macroscopically distinct, we'll come back to that, one of these two states is actually realized even when we don't look at the system. This is very crudely the scheme by which the system works. You start the system off in a state which is, say, the plus state, the anticlockwise circulating current here, and you let it evolve for a time, and then you measure it to see which of these two states it's got to. And remember, we can do this, in fact, in real life. And then we let it proceed by itself. And we find that if we do that for appropriate values of the time and so forth, then we have an equal probability of ending up at a final time, either where again we can measure, or we have an equal probability of ending up here or here. So in other words, when we look at it, it can go to either of these two. Again, if we actually measured it to be in this state, then we find it can go to either of these two. However, let's now not measure it at this intermediate time. Then what we find, crudely speaking, is that it always ends up in the minus state and never in the plus state. So how can that be? Well, of course, the first thought that occurs to you is that, well, maybe when we made the measurement, we somehow influenced it in a way we don't want to. But we actually check that, at least to some extent, by performing the measurement at a time when we knew for sure, and when quantum mechanics says, say, and we can actually confirm experimentally, that it was most certainly in this state at the intermediate time. So we can do a set of ancillary measurements to check that. Of course, all this is, there's a lot of technicalities associated with this, but crudely speaking, we can actually do that experiment. That experiment had actually not been done until December of 2016. What had been established was that if we interpret the raw data in this kind of experiment in quantum mechanical terms, then in fact the intermediate state should have been one of these weird quantum superpositions which both Steve and Bill talked about. But remember now, this is a quantum superposition of two states which are pretty different actually. They have a circulating current of maybe a few microamps, say, clockwise or anti-clockwise. And you can try to work out, is that, well, how close to the everyday level is this? That's a complicated issue, which is discussed in this particular archive paper. But very crudely speaking, I would myself claim that this experiment is at least as macroscopic as an experiment done with the smallest speck of dust that you can actually see with the naked eye. So we really are quite a way from the microscopic to the everyday level in this experiment. So, well, in December of 2016, indeed, this experiment was done, and indeed it shows, with all the complications and provisos that one has to make, of course, but it does show, crudely speaking, that indeed that macroscopic object was not in a definite one of its macroscopic states when we didn't look at it. Well, what do we actually mean by saying that it was, or making the hypothesis say it was or was not in one of these states? Again, well, I think this is reminiscent of a statement which was made in a rather different context, but has become rather famous or notorious. It all depends what the meaning of is. What do we mean by saying that it is in the plus state, say? I think, again, we have to conclude that all we could really have meant is that had we actually looked at it, say with the naked eye, we would have seen it to be in this state. So basically what we have shown here is that macroscopic counterfactual definiteness is refuted not just in experiments where it's sort of generated at a microscopic level, the level of photons and so forth, but also at this really pretty everyday level. It simply is not the case that had we looked at it, we would have seen, say, the plus state. Well, that's a bit of a problem, I think. Let's have the next slide, please. So this actually raises the question, do counterfactual statements have truth values? Well, before we discuss this briefly, let's just note that not only does common sense assume that counterfactual statements have truth values, but so very, very emphatically does the legal system. For example, the prosecuting counsel may say to the jury, had the accused not pushed his victim down the stairs, she would still be alive today. And the jury has to decide whether they think that statement is true or not. And their verdict and their sentence and whatever may well depend on whether they decide it was true or not. However, we physicists are not the first to have worried about this question. The philosophers have been worried about it long before the birth of quantum mechanics. And here is one view, which I'm told is quite popular in the among the sub-community of philosophers who worry about these things. From a book by David Lewis called Counterfactuals, there's something like this. If kangaroos had no tails, they would topple over. He says, seems to me to mean something like this. In any possible state of affairs in which kangaroos have no tails, and which resembles our actual state of affairs as much as kangaroos having no tails permitted to, the kangaroos topple over. So, can we apply that here? Well, is it the case that in any experiment in which everything else is the same, but we measure A instead of A prime, then we'd always get, say, +1? Unfortunately not, for actually for more than one reason. First of all, one can't always be sure that everything else is the same. That's the so-called hidden variable problem. And secondly, even if it is the same, we don't always get the same result. In other words, there is, or does appear to be at least, a fundamental indeterminacy or indeterminism rather in quantum mechanics. And the point I want to make is that this state of affairs, we can now say, I think, on the basis of this NTT experiment, that's the 2016 experiment I mentioned briefly on, which incidentally I am a co-author, though a rather minor one. This experiment shows that that's not simply the amplification of a microscopic indeterminacy, it's true even at a semi-macroscopic level. So that raises what I think is quite interesting quasi-philosophical problems, and I think possibly slightly counter to what Bill said. I do think that sometimes philosophical problems do enter physics and are quite interesting when they do. It raises, for example, the question of whether determinacy is even possible in the absence of determinism. That is, if we can't be sure that, as it were, the same, everything else is the same, would always give the same result, then we may not be able to assert the principle of determinacy. But put aside for the moment the question of how we approach this from the side of philosophy. I think what we can now say is that not only at a microscopic level, but even at this level, which is getting really rather uncomfortably close to our own human experience, we may eventually have to conclude, and could I have the last slide, please? That even at the everyday level, there really is no such thing as would have. In other words, counterfactuals really don't have definite truth values, and that, I think, is getting uncomfortably close. And 100 years from now, maybe, the legal system and other evidently macroscopic everyday level institutions are actually going to have to take account of that. So I think it really is rather interesting that Bell's theorem, which was originally formulated at the level of single photons and so forth, way at a level very many orders of magnitude distant from our everyday life, now is actually going to come up and bite us in our everyday life. Thank you.
Well, thank you very much, Tony, for that provocative talk. And certainly I would say that if the American legal system one day takes account of quantum physics, whereas right now it doesn't even always take account of logic, that would be a remarkable move forward. But no doubt your talk will generate a number of questions in the discussion session. But as time is a bit short, let's move right on to the final speaker for today, Professor John Mather, who is a senior astrophysicist at the NASA Goddard Space Flight Center and adjunct professor of physics at the University of Maryland. He shared the Nobel Prize in 2006 for the discovery of the black body form and anisotropy of the cosmic microwave background radiation. So, John, the floor is yours.
Thank you. Thank you. Well, I hope I have less trouble with technology here, but I'm going to try to share my screen with you and show you the story of the universe, which I think is one of the more important discoveries that we made in the 20th century. And so I think I will argue that what I'm going to tell you is actually a combination of applied quantum mechanics and thermodynamics. But before I get into that part of the story, I just want to show you what I'm working on now. This is the Great James Webb Space Telescope as it will be in outer space in October of 2021. We are planning to launch it just over a year and a bit from now. So coming soon, after almost a quarter century of work. So this is a joint project of Europe, Canada, and the United States and our 3 space agencies. And if you're an astronomer, you will be able to use this telescope by sending us a proposal about how to use it. So just to give a little hint about what this telescope is, it's our observing tool to look back in time, to see the history of the universe. And what we see here in the middle is a gigantic golden hexagonal mirror made out of 18 pieces. And the telescope is 6.5 meters across, the aperture of that great mirror, which is larger than the rocket that will carry it into space. And it is protected by a 5-layer umbrella, a 5-layer sunshade. This big set of 5 gray sheets in the picture, about as large as a singles tennis court, to keep the telescope cold in outer space. So we'll get back to it a little bit later, just to show you what we hope to do with it. But just this is the introduction. This is why I'm excited about the history of the universe, although I think I've been excited about it since I was a child. So let me see if I can get this to work. So how did we get here? Well, as we've already heard, quantum mechanics determines everything. And though you can't really apply Schrödinger's equations to concrete, if you could, you would be able to calculate what it does. Engineers find that it's easier to build and measure than it is to calculate. But at any rate, there's really not much doubt that every atom, every molecule, every living thing that we interact with is governed by quantum mechanics on all necessary scales. So we are presumably made out of little Lego bricks, the atoms and molecules, and the way that they fit together is entirely determined by the quantum mechanics and those wave functions that we've been hearing about already. So although it may take a special experiment to make the wave nature of things visible, in fact, everything you look at, your entire body is a representation of all of that. So we know that the universe is expanding and that it was very smooth and very hot when it was young. This was discovered, as I'll show you, back in 1929, although there was already evidence of it even before that. We know that it has been very unstable. The balance of nature, it does not exist. There's no such thing as the balance of nature. There is the instability of nature, and I'll show you a few examples. The universe is extremely large, probably, according to our guesses, infinite, which means there's no edge, and the volume adds up to more than any finite number. So the universe is also old, about 14 billion years old, which means that even very unusual sounding, seemingly unlikely events can occur. So people think, well, of course, life, such as we represent, must be very unlikely in the universe, but here we are. So a very low probability has nevertheless been realized in ourselves. We have learned about how this all works because of stored information. And we've even learned about the connection of stored information with thermodynamics, the relationship between a bit of information and a fundamental constant of thermodynamics. So we've learned about that. We understand something about complexity, evolution, survival of the lucky, as I call it. When Darwin gave us the idea of evolution, people thought, well, survival of the fittest, and it was very easy for people to say, well, of course, we are the fittest, we are the top of the pyramid, we human beings are the pinnacle of everything, the entire universe has been aiming towards producing us. I think now we should have a little more humility in the face of the changing environment, and we are more, I would say, lucky to be here than we are the aim of evolution, particularly now that we see the changing environment threatening our own existence coming back. We've learned about nested feedback loops and control laws. Biologists are telling us that, well, most of the atoms in our bodies have been replaced many times. Nevertheless, we are still here. We still remember what we had experienced when we were younger. And this is called by them homeostasis. It means that the system that we are is maintained in its general form by the incredibly complex little atomic control laws that are working to stabilize every single cell or to replace every cell when it dies. So this is a totally astonishing story of biology, which is 100% dependent on the quantum mechanics that we've just been hearing about. So instability is one of the themes of cosmology, the expanding universe. So in 1902, Sir James Jeans told us how to calculate when will a cloud of gas, interstellar gas, be able to pull itself together and turn into stars. So basically, he said, if the gravitational force of the cloud on itself is bigger than the pressure of the gas that's holding it up, then it can possibly collapse and turn into stars. So 1902, we learned how to calculate that bit. And by the way, astronomy is a place where we recognize self-heating objects. In ordinary chemistry, we say, well, we put something together and it gets hot because of a chemical reaction. But in astronomy, we say something get hot when gravitational energy is converted to kinetic energy and then into heat. So the universe has been self-heating along the way because of these kinds of instabilities. So how does this apply to our lives? Well, we are an emergent non-equilibrium phenomenon. As an example of one that we don't require human life to interpret, here is a picture of the Hurricane Harvey as it was pouring down over a meter of rain onto the Johnson Space Center in Texas while we were testing our great telescope in the vacuum tank there. But this is an example of a spontaneously occurring heat engine. It draws energy from the equator of the Earth and transports it to the pole so that it can be radiated into outer space. And in so doing, it supports this gigantic whirling form, a kind of organization that can extract energy from a gradient and produce more entropy. So human beings do the same thing. We are able to extract energy from our environment and produce more entropy than we would have had. So this is an example of a fundamental principle of physics which we're getting to be more aware of now. So now I want to step back to a few more elementary things, because in the 20th century we learned how to look back in time in a very quantitative way. We learned how to measure the speed of light very precisely. And it is now measured so precisely by atomic physicists that we've decided, instead of measuring it anymore, we're going to define the speed of light and define the meter and the second in terms of atomic vibrations. Nevertheless, and for astronomers' terms, we just use a pretty round number. We don't care about those details. So here we are suggesting that we can look back in time almost all the way back to the Big Bang, as we call it, by looking at things that are very far away. So how far away are you looking? You need to survey the universe. So we use two basic methods. One is geometrical and one is photometric, using the brightness of starlight. So if you can draw a triangle, as we have in the upper picture here, and you know one of the lengths of the triangle, and you know the angles of the triangle, then you can calculate the whole shape of the triangle. So that's surveying. And we can do that for objects that are relatively nearby in the solar system, in our own galaxy, and now with the latest technology, using the European Gaia Observatory, we can extend that out to some of the nearest galaxies. The other method is called the standard candle method. If I can see two different objects in the sky, and I promise you that they really are the same, just one is farther away, then we can get the ratio of distances from the ratio of brightnesses. So now we can survey the distances to everything in the universe by these two methods. And now we'd like to know about motion. So ordinarily, most objects do not move quickly across the sky, so you can't tell much about their motion. But there is one thing that we can do, which is given again by quantum mechanics. In the upper left picture, we illustrate here that a glowing gas can have the vibrations, the atomic vibrations can come out and emit particular special wavelengths that we pick up in our instrumentation. If you go to a fireworks display, the special colors that they give you are because of particular chemical elements that they put in those little explosion materials up there. So we can see these same kinds of evidence in the starlight. So we can even detect chemical elements in the surfaces of stars. One of them, helium, was detected in this way. That's why it's named after the sun. At any rate, for this purpose, we'd like to know whether the object is coming toward us or going away from us. So the way that we tell is we look to see what is the spectrum. We spread out the starlight with a prism or a grating to get a nice little rainbow. And what we'll see is that quite often a nearby star has just about the same spectrum as its similar neighbors. But if we look at one more distant, all of the wavelengths will be multiplied by some number larger than one. And we'll say that's because that star or galaxy is going away from us with some speed. And we can calculate that speed and calculate many more things about it. But from this, we were then able to discover the expanding universe. So here is a picture that Edwin Hubble drew us in 1929. The little dots on this graph are galaxies, and in the horizontal axis is how far away he said they were. On the vertical axis is how fast he said they were going away from us. And there's a trend here. You can quite clearly see that if they're far away from us, they're going away faster than if they're nearby. So if you say, well, this is well described by a straight line, then I should be able to calculate how long did it take for all of those objects to get there from the original case where they were all together. So divide the distance by the speed and you get the age of the universe. Back in 1929, his value was about 2 billion years, which was bigger than anything we'd ever measured before. It's the first time we actually thought seriously that the universe had an age at all. Now, as it happens, he was wrong about that because the standard candles that he was using to estimate distances were not actually the same kind, the near ones and the far ones. Another interesting thing to note here is in the lower left corner, there are 4 objects that are actually coming in our direction, coming toward us. And those are going to be very exciting in the near future. In a few billion years, these objects will come and meet us. So it'll be fun. So 1929, by the way, Hubble was not the first one to understand this. It was predicted independently by Alexander Friedman in 1922, and then again by Georges Lemaitre, a Catholic priest, in 1927, both of them using Einstein's equations, and Lemaitre also using some of the observational data to say, yes, indeed, I think the universe is expanding. So 1929. So this is a big surprise, a huge surprise. Nobody was expecting this. Einstein was sure this could not occur. In fact, he had already changed his equations of relativity so that he could make sure that this would not happen. Nevertheless, it does happen. So Einstein was wrong once. It happens. So in 1948, it was calculated, after we'd fought a war and learned how to do nuclear physics, that the universe should have been very hot when it was young, and that we should be able to calculate from that idea that the universe should be filled with heat radiation now, and that we should be able also to get the chemical elements distributions from the nuclear physics. So indeed, that idea is now called the Big Bang. In 1948, it was not yet called that. The 2 gentlemen, Alpher and Herman, who predicted this radiation should exist, the heat radiation, did not get anyone to go measure it. So they did not get their Nobel Prize for the great prediction. That came later for the people who were not looking for it, but did discover it, Penzias and Wilson, who saw it in 1965. So this cosmic heat radiation fills the entire universe. It is left over from those very first hottest moments of time, and it still exists and we can measure it. So in 1974, a team was formed, inspired by many experiments that had gone before, including my own failed thesis experiment at Berkeley. So we said, let's go measure that radiation a lot better. We proposed to build a satellite that looked like this. It's called the Cosmic Background Explorer. It took about 15 years to get it up into space. And what it did was to measure that cosmic heat. So within a few weeks, we had our first measurement. This is the spectrum of the cosmic microwave background radiation. It's called microwave because the brightest radiation is at a wavelength of a few millimeters to a few meters. And so that was how it was first detected. In this picture, the theoretical prediction is the smooth curve, and measurement as the little boxes, and you can see they're all right on the curve. When we showed this chart to the American Astronomical Society, we got a standing ovation for this chart. So why does people care so much about that chart? It proves basically that the Big Bang story explains the data. The universe was hot when it was young. It was in a kind of thermal equilibrium with itself. So this curve has only one adjustable parameter. It is the temperature, which we now have measured to be 2.725 Kelvin, although it was trillions of degrees when the universe was young. So number 1 result. Number 2 result came out 2 years later. And the picture in the lower right is the one I want you to think about. This is a map of the entire sky as observed with the cosmic microwave background radiation. So it is covered with little pink and blue blobs in this picture, which represent tiny variations of the temperature. So the variations are very faint. The temperature itself is about 2.7 Kelvin, and the amount of change that we see from place to place is about 1 part in 100,000 of that. So when Stephen Hawking saw this chart, he said that was the most important scientific discovery of the century, if not of all time. And I was really thrilled that he liked the chart. But I think now I can tell you more about why it was so important to people. So number one, we think that those spots represent density variations in the early universe of about a part in 100,000. And number two, that gravitation acting on those spots is able to produce the galaxies and stars that we now see. So if the universe were absolutely totally smooth and homogeneous, even as it expands and cools, it would not have had time to produce galaxies and stars. So it had to have primordial seeds in it, and these are those. Second thing that we now say about those spots is most of them come from the cosmic dark matter that was mentioned earlier as one of those things we cannot yet explain with quantum mechanics. We've even found cosmic dark energy, which is part of this story as well, which remarkably enough explains, which remarkably enough tells us that the universe is now not only expanding, but going faster and faster at all times. So the combination of these two charts got us a second Nobel Prize for the expanding universe. The first one being for the discovery of this background radiation, that was Penzias and Wilson. And a few years later, a third Nobel Prize was given for discovering this cosmic dark energy, which I'm not going to explain because its time is short. But it has turned out that the expansion of the universe was worth three Nobel Prizes already, and there might be more when we finally figure out what made those cosmic spots. There's a challenge hidden in these cosmic spots, which is quantum gravity. We do not know why those spots are there. One idea would be that that's the thermodynamic fluctuations of quantum mechanical material of the early universe. And wouldn't it be cool if we had a theory that explained not only that they are there, but exactly how bright they are? When that happens, I think the committee in Stockholm will be very interested. So what do we do next? Well, we have now a story of the early universe. We have a story of the gravitation pulling things back together to make stars. Now we have a story. Here's a summary of the standard picture I'm going to tell you. It's not the only picture that we have, but we say, well, okay, well, the universe was very hot and very compressed when it was young. It has no center that we can see, although it feels to us that we are the center because everything is rushing away. We are not so brave just to say that we should be the center. We have seen no sign of any other center, nor have we seen any sign that there's an edge. So that means that the universe is probably infinite, though you can't prove that. That is expanding into itself. Even means that there is no first moment. Time of equal exactly to 0 is not included in this story. We can tell you as you run your imagination backwards in time that as you get to higher and higher densities and higher temperatures, that eventually we run out of the laws of physics and we have no idea what should apply. But you cannot actually get all the way to time equals 0, just as you cannot find the smallest positive number. So that means there is actually not an instant of creation, although people have said there was, and there's not a big firecracker. Although when you call it the Big Bang Theory, most people think of a firecracker. So we have Sir Fred Hoyle to thank for that misinformation. He didn't like this expanding universe story, and that was the name that we got stuck with. But it conveys exactly the wrong idea. So I'm sorry about that. The world has been confused, including many scientists about the expanding universe, but this is my version. So now what are we going to do? Let's go measure. Of course, astronomers say we do it with telescopes. Here is the Hubble Space Telescope, which is already 30 years old, and it's still functioning beautifully and probably has another 10 years of life because we have been up with astronauts 5 times to upgrade it and make it better, and it is still very happy in space and answering astronomy's prayers for a long time. So we now have a story, we have the ability to test if it's true, and we have computers which give us a time machine. So if you say, I gave you the right story just now, then I should be able to put a calculation into the computer, simulate the expansion of the universe, simulate those hot and cold spots turning into galaxies. So I have a movie that was made with supercomputers that illustrates that. And it's a beautiful movie. Here we give a picture from Hubble just to say this is what we have to check the movie against. The time machine I want to show you is in this movie. So here we imagine a box of universe. The computer scientists have made it rotate in front of our eyes with gravitation acting on this expanding universe. Of course, the computer folks can say, let's pretend it's not expanding so we can draw a picture of it. So what we see is that even within the first billion years, the gravitation has pulled things together into great strings and sheets of material, and galaxies are already starting to grow very, very quickly in early times. That's not exactly the way astronomers expected it. When the Hubble telescope was built, people were very sure that the galaxies must take a very long time to grow, but they were almost completely wrong about that story. And now if you look at this picture, at this moment, you see that gravitation has pulled the material not only into galaxies and strings of galaxies, but sheets of galaxies in a three-dimensional structure, huge flat things surrounding vast empty regions that we call cosmic voids. So after a few billion years, we see huge explosions occurring in the cores of these galaxies. So explosions can occur for multiple reasons. One of them is stars get old and they explode. One of them is that black holes can form and material falls in and becomes very hot on its way in and releases huge amounts of energy as it does so. So in this picture in this movie I'm showing you, after about 9 billion years, the solar system would be born in the outskirts of one of these little galaxies out here. And well, I guess in a way it's lucky that the solar system was not born sooner, because we might very well have been disturbed by those huge explosions that you were seeing in the movie before this. So this is a movie which might or might not be true, at least in a kind of statistical sense. So needless to say, although this shows you that the progress of 14 billion years in front of your very eyes, we need to make sure that it tells the right story. So more telescopes, more pictures are required. So after the Hubble telescope was built and launched and operational, people did write us a little book that said, that was great, please build us another more powerful telescope so that we can really see the very first galaxies being born. So that is becoming the James Webb Space Telescope that I showed you at the beginning. So what has happened after that? Well, of course, we need to don't want to show the movie again. So here is a beautiful picture of a spiral nebula taken with the Hubble Space Telescope. And it's a beautiful picture showing 2 galaxies nearby. And I love this one because here's a picture made by an Irish astronomer in 1845 who had built a telescope almost 2 meters in diameter with a giant metal mirror, and he had to climb up on a rather dangerous high ladder to look through the eyepiece, but he was able to draw something very much like what we see with the Hubble telescope. It's an astonishing accomplishment for almost 2 centuries ago. At any rate, beautiful picture. If the solar system were in this spiral nebula, it would be way out on the outside and be very hard to detect. By the way, these 2 galaxies in this picture are going to merge together in the next few 100 million years, and that will be a very spectacular event for the inhabitants of those galaxies. So another part of our story, how did we get here, which is the big question I asked at the beginning. We need to have the chemical elements of life here on Earth in order for us to be here. So this is a picture taken with the Hubble Space Telescope of the Crab Nebula. The Crab Nebula is a star that exploded on July the 4th, almost 1,000 years. Almost 1,000 years ago on AD 1054. So we see the chemical elements of life all the way from helium, hydrogen, helium up to iron are in this particular nebula flying apart into space. It moves fast enough that if you take 2 different pictures with the Hubble telescope, you can see the little bits have moved from one year to the next. By the way, also, we know now from the LIGO observatory that the source of the heavier chemical elements, all the way up to uranium, plutonium, gold, and so forth, is not this process, but is the merging of two neutron stars. So our own particular history is based on rather catastrophic and cataclysmic events in space, of stars blowing up, stars combining to form black holes, and we're here because of them. A totally astonishing history of the basis of our own existence. So how do we know this is true? Well, the next step is, can you see solar systems being born? And the answer is yes, now we can. Here is a telescope that has been built in South America. It's called the Atacama Large Millimeter Array. It is up at an altitude of 5,000 meters in the desert, in a place where it did not rain for 500 years. At any rate, a very wonderful place to put a telescope. And they were able to make this image in the upper left corner of a new star surrounded by orbiting rings of dust grains. So it's just like the rings of Saturn, except this time we think there is so much dust there that it is actually turning itself into planets. So we see the dark rings in between the bright ones. Those are thought to be places where planets are growing and absorbing the dust. So if you were to come back in 100,000 years, we think the most of the dust would go away and we would be left with about 9 planets in that future solar system way out there. So it is possible that this is how solar systems are born, and maybe how our own solar system was born. So we're still working on that problem, but we're getting there. So more to be learned. So I'm going to wrap up with a little bit about the James Webb Space Telescope itself. Here we show a few of the things we're going to try to observe. We mentioned NASA, European, and Canadian space agencies. This is where I work at Goddard Space Flight Center in Maryland, just outside Washington, D.C. We have one giant contractor called Northrop Grumman Aerospace Systems, and we have instruments from Europe and the United States and Canada that are all combined inside this equipment. It is going to be operated from the Space Telescope Science Institute in Baltimore, just as we run the Hubble telescope. And it is a spectacular thing to see this glorious golden telescope in its clean room with the technicians working on it. By the way, the European Space Agency is contributing the launch vehicle, the Ariane 5 rocket. So when we push the button in October next year, we will be in French Guiana, where the Ariane rockets are launched. We are carrying fuel for about 10 years of mission lifetime, and we are aiming for many, many wonderful observations, tackling questions like, what was the first object that formed after the Big Bang? The first stars that lit up? The first black holes that formed? How did the galaxies like the Milky Way grow from little bits? Probably. How were the stars and planets born? We know many places where it's happening, but we can't see very well without better equipment. How did the planetary systems like the one that I showed you originate? And can we actually see the planets? Are any of them like Earth in any way? We know that some of them are out there. We know that planets are very common. Most stars have them. About 20% of stars have planets about the right size and temperature to be like Earth. But are they like Earth? Well, we'd like to know, and we need more measurements. So we will be working on that one with this telescope. So if you're an astronomer, by the way, you should be thinking about writing your proposal, because observing proposals are due on November 24th, just a few months away from now. So coming soon, this great telescope in space, which is, by the way, so powerful that if you were a bumblebee, a small insect hovering at the distance of the moon away from the telescope, we would be able to see you both from reflected sunlight and from the heat radiation that you would be emitting as well. So it's astonishing how powerful this observatory is, and we certainly expect to be surprised by what it shows us in space. So that's part of our story of where we came from, and why I think the recognition of the expanding universe is one of the great discoveries of physics of the 20th century. We would not have a story about how we exist without that bit. So then we get to the next question: how does biology work? So this is quantum mechanics again. Molecules stick together in the way that they do because of quantum mechanics. we have a lot to go before we really understand this. As this cartoon suggests, we don't know. We do, however, know that it's complicated. It did happen once, at least here. We are, as astronomers, switching our position to think that probably it happens elsewhere. And so it's worthwhile looking. So we will certainly be looking at planets around other stars to see if there are signs of oxygen, a sign of photosynthesis, or water, at least to make such a place habitable in principle. So coming soon, we hope to be able to tell you, are there other places in the universe that could support life? So wrap up here, and I guess now we'll switch to having some questions for all of this panelists. So thank you, and I give you back the control of the computers. Here we go.
Thank you, John. Appreciate that wonderful talk. And as you said, we will now bring in the three discussants to have a question session. They are Professor Jocelyn Burnell, who's a visiting professor of physics at the University of Oxford and was the first person to observe radio pulsars in 1967. She was awarded the Special Breakthrough Prize in Fundamental Physics in 2018 for her discovery of pulsars. Also joining us is Professor Jim Gates, Jr. Professor Jim Gates is the Ford Foundation Professor of Physics and Theoretical Physics Center Director at Brown University. He was awarded the National Medal of Science in 2013 for his contribution to the mathematics of supersymmetry in particle physics, in field theory, and in string theory. Professor Chung-Pei Ma is the Judy Chandler Webb Professor of Astronomy and Physics at the University of California, Berkeley. She was awarded the Maria Goppert-Meyer Award by the American Physical Society in 2003 and led the teams that discovered several of the largest known black holes between 2011 and 2016. So welcome to all of the discussants, and let me turn first to Professor Jocelyn Burnell for the first question.
Sorry, am I asking a question or answering a question?
I believe that you're asking, but if there's a question that you'd like to answer, we'll be more than happy to hear that as well.
No. I actually wanted to make a point rather than ask a question.
Sure.
We've had quite a bit of emphasis on thinking outside the box, and that's very important. But in addition to thinking outside the box, we've got to be able to see outside the box, to see the things that you don't expect to see. And that's often where the breakthroughs come through. We can be awfully conditioned by what we think we ought to see.
Do you have a specific example in your own career where that kind of thinking was essential?
No.
All right, so let's turn to Jim Gates. Comments, reflections, questions, anything is welcome.
I'd like to extend my thanks, obviously, to all of us, the members of our panel for those wonderful talks for those of us who are caught in this business of thinking about the universe via the lens of our minds and mathematics and observation, because that's what physics is all about. So I found it very interesting that 3 of the 4 presentations really were directed towards thinking of what quantum mechanics has done to us as a species, trying to figure out this thing that we live in called the universe. And so there were 2 points that I found especially interesting. One of them, and as I said, these points were woven through 3 of the presentations, and even in the final presentation, we saw elements of it. So the first element was this whole question about the nature of reality, and which came up in several different ways. One of them was the so-called demarcation problem. That is, how do we tell what's science and what's not? I think it was Bill who gave this answer about the interpretation about what, it depends on what we can measure, and I think that's the right thing. The other thing that I'd like to hear all 4 discussants speak about is the role of information, because for the part of physics that's been looking at black holes, our focus has been on what happens to the information that's contained in nature. And in my own research, I have found information theory popping up in an extraordinary way when we start thinking about this property of supersymmetry. And so I'd like to know where that fits in the discussion And I mean the kind of digital information in terms of bits. Where does that fit to the discussion that Steve and Bill and also Tony had in terms of thinking about these weird properties of quantum mechanics? And then I'd like to direct a question to John that he could probably engage better, is that why does he think it is that we, our species, people, seem to be right in the middle of these two extremes, of the extreme small and the extreme large?
Anybody want to take the first question, Steve or Bill? Bill, yeah, your hand's up. Please go ahead.
Sure. Well, in answer to the question about information, first of all, I don't have a good answer, but I want to affirm how great a question it is. One of the things that we are having a great deal of fun with right now is quantum information. And one of the, I wish I had time to describe exactly what that means, but, information stored in quantum mechanical objects rather than in macroscopic objects like CD-ROMs and magnetic memories, but instead in individual atoms or similar quantum mechanical objects. And one of the pieces of fallout from thinking about quantum information is we're actually beginning to teach quantum mechanics from an information point of view rather than in the more traditional way. And all kinds of wonderful new perspectives come up when you think about quantum mechanics from an information perspective. And one of the things is one that Jim already mentioned about what happens to information when it falls into a black hole, and ideas of quantum scrambling, as it's called. And we're able to actually do experiments in the lab that can reproduce in a kind of small way what this process of scrambling and the apparent loss of information, which never seems to really go away, that happens under those circumstances. And while I have no good answer to any of these questions, it has opened up a lot of really fun new directions for research.
Steve or Tony? Steve, go ahead, please.
Well, at the risk of getting a little technical, I think the future of quantum mechanics may lie in a direction toward information theory. There's an object called the density matrix, which is central in information theory. It's not just describing a system in terms of a wave function, but all possible wave functions with probabilities for each. And it's possible, for example, the entropy of a system, which is a fundamental quantity in information theory, is simply related to a mathematical operation applied to the density matrix. It turns out the density matrix evolves in a way that goes beyond quantum mechanics. It's called the Lindblad equation, which is necessary in order for the density matrix to remain sensible as a density matrix. And I think one possible direction for the future evolution of quantum mechanics is as a theory not of the evolution of the wave function, but of the evolution of the density matrix. Unfortunately, I haven't quite seen to the bottom of it.
I agree. I don't think we really understand the role which information plays in quantum mechanics very well. There are indeed some interpretations of quantum mechanics which essentially simply say the wave function or the density matrix is nothing more nor less than a description of the information which a particular person may have of it. Then you get into some rather interesting conundrums or possibly paradoxes, particularly associated with the so-called Wigner's friend thought experiment, where different people, different people who are taking part in the experiment may have different bits of information, and can you put them together in a consistent way? So these things are still very much a matter of discussion, and I don't think that we really have an agreed understanding of them.
Yes.
John, any thoughts on the other question to do with where we humans fit in the scales
Yeah.
of the universe?
Yeah, so how come we're here and we're not bigger and smaller? I think if you were to say, we don't know humans exist, we only have the laws of physics, we would probably not notice that this is a possibility, that as we are sort of, as I said in my story, spontaneously derived heat engines. And you can't always tell what's going to happen until you see it. So if you didn't know hurricanes and tornadoes could exist, you might not get them unless you could at least run a supercomputer to simulate them. So just standing off from a distance, it's pretty hard to say we should be here at this particular size scale. So why is the scale of an ant not big enough for a human civilization? I don't know. They have a pretty astonishing cooperative arrangement that they do. So why do people have 2 legs and most creatures have 4? There are a whole lot of sort of what if questions, which all come out to be, well, it's about right here. But I think because we are the ones asking the question, we always say, well, we're the right size.
Professor Ma, any thoughts, reflections, questions?
Sure. Yeah, thanks for sharing your wisdom from the smallest to the largest scales of the universe. I'd like to follow up a bit on what John said. To make sure we are telling the right story about how we get here, obviously we need to solve 2 unsolved mysteries. What is dark matter and what is dark energy? For dark matter, we know a lot about what it cannot be, right? We know most of it needs to be non-baryonic. It can't be, so it can't be typical faded Death Stars like white dwarfs or astrophysical black holes. Standard model neutrinos are finally found to have mass, but we have strong constraints on their role as hot dark matter. And ironically, they can only account for a sprinkle in the cosmic budget of dark matter. And there's a surge in interests in axions as alternatives to WIMPs of dark matter candidates. As for dark energy, we know even less. And none of this is due to a lack of efforts. Large galaxy surveys are being conducted to measure the equation of state of dark energy. And thousands of dark energy papers have been published. I don't know if theorists have shut up, but they have certainly been calculating. So obviously pinpointing what dark matter and dark energy are would be great discoveries of this century. So for example, is the detection of WIMPs or axions just around the corner after decades of searching? Are we actually on the right track? What more will we be able to learn about dark energy beyond its equation of state? So my thought right now is when fascinating meetings like this is held in 20, 30, 50 years again, I wonder what kind of discussions will be held then.
It's a great question. I might also add to it that it's remarkable that even though we don't know what dark matter is and what dark energy is, we know how much there is. And indeed, one member of the 4-person Nobel panel here made a prediction, in essence, for the amount of dark energy before it was even discovered that there was such a thing as dark energy. So does anybody on the panel have any thoughts on how close are we, or when we might have insight into these key questions regarding the dark side of the universe?
Well, when the superconducting super collider started up, a lot of us were hoping it would discover the particle that would stand out as the obvious dark matter particle. And it hasn't happened. And unfortunately, we can't promise the funders of accelerators that it will be discovered if we just increase the energy by a certain amount. So, you know, the dark matter problem solution is just around the corner, but that may remain true for a long time to come.
Other thoughts on the dark side of things?
Yeah, this is John. I think there's nothing in our understanding tells us that this should be easy. That nature is cooperating with our desire to detect something. It could very well be that in 1,000 years, we still will never have detected a dark matter particle or anything further about the dark energy except its equation of state. We might get lucky. Maybe we'll have a good guess at a theory of quantum gravity that says there should be some other consequences of the dark matter and the dark energy. But right now, they sort of stand separate and they have no observable consequences in anything except astronomy yet. Maybe they will. Maybe atomic physics will say, oh, well, there's some little energy level splitting that should be due to one of those things, and we'll find it, but maybe not.
Did want to get to at least one or two questions from the general public audience that's here. So I wrote down a couple names of questions that looked interesting. I don't know if these individuals are still on Zoom, but Margaret Hartle, if you're still here, please feel free to ask your question.
Thank you for the amazing event. I have actually submitted loads of questions because it's such an amazing opportunity to be able to listen to you guys. So I'll ask my first one really, which is from your understanding of the current state of physics, in what area of physics are you expecting the most profound discovery or reframing of our worldview to occur? And if I could ask the follow-on question from that about the methodology, I've always been fascinated by this unreasonable effectiveness of mathematics statement. And I always wanted to ask people who I hope could give me a good answer, whether you think that if we could prove mathematically something, you know, rigorously without doubt, but never be able to prove it by experiment, could we take that as a given?
Steve, you want to take that first shot at that second question?
Well, mathematics by itself can prove nothing of the real world. It's not, it's a kind of language, a logic. It doesn't in itself have any information about reality. We may be, however, in a position where we have a theory, some further version of the standard model that makes predictions that we can't test, but which we believe because they follow as mathematical consequences of a theory that has been tested experimentally very well. And I'm thinking particularly of the idea of the multiverse. Many people have challenged whether thinking about a multiverse is science at all because we can't ever observe the other sub-universes. And my attitude is that if we can show mathematically that it exists as a consequence of theories that have been tested, then we will believe it. Just as we believe for many, many centuries that the moon had an opposite hemisphere, even though we couldn't see it, because it made sense theoretically in terms of things that we could observe.
Thank you. Other thoughts on Margaret's question? Margaret, by the way, apologies for mispronouncing your surname. Any other thoughts on Margaret's questions from the panelists?
Yeah, I just wanted to say that I agree with Steve on this point, but we have a second step to go through, which is to say, yes, that story is the only one that fits. And that's a harder question. We did get the prediction that there should be antimatter from the equation from Dirac about electrons, and it turned out to be there. If I were a theorist, I would probably produce many more wrong theories than correct ones. And so that's our job, is to sort out which ones are the right ones from which ones are the wrong ones. And so if we do get to one where we say, yes, this is the unique theory that explains what we've got, then maybe I'll believe in the multiverses.
I think Professor Jocelyn Burnell has a follow-up thought on that. Please go ahead.
Another thing I think we need to look out for, we're just at the beginning of the study of gravitational radiation. A whole new spectrum is opening up. We are probably going to find things we have not dreamt of. we're probably going to get data on things we thought we knew about that contradicts what we know about them. So I think there's a lot wide open at the moment, very wide open.
Yes, Bill?
I wanted to mention that in the context of Margaret's question, there is another feature which is quite common today, becoming more and more common, that is in a sense the kind of mirror image of the sort of thing that Margaret said. That is, we have many situations where we have simple theories that when applied to real world systems are so complicated to calculate that we do not have the ability to calculate the answer, even though the structure of the theory is quite simple. We can't perform the calculations to find out what the theory in fact predicts. We know what nature does, but we don't know whether the model, the theory that we have to try to explain what's going on actually does explain what's going on, because we can't do the calculation. So you see, it's sort of the mirror image of the idea of being able to calculate something that we can't measure. Here's something where we can't calculate something that we can measure. And this is the problem of complexity, which often applies to, for example, quantum mechanical systems when you have more than a handful of interacting objects. And I believe that we're on the threshold of making some real breakthroughs in that area. And I think that's going to be really exciting.
We're running a bit short on time. Let me ask if there are any other thoughts from our discussants who joined us after the Nobel panel. Jim, one final thought?
Yes, I want to pivot on the comment that Bill just made. Many of us are actually starting to harness the power of IT and information technology and computers at a level that I've never seen in physics before. Even in something as abstract as string theory, there are some of us who are undertaking calculations that involve billions of functions. But with this modern information technology, it is as if we have a better pair of glasses to look deeply into the mathematics that Bill was just discussing. And I think this is going to be an increasing trend where we theorists, those of us who aren't directly looking at measurements, I think we're going to rely more and more on computation to extend our mathematical reach. I tell people it's like putting on the Iron Man suit, but in the mathematical version. You get so much power over the equations that were not there before.
Yeah, I mean, I would second that thought, certainly, as a fellow string theorist. The kinds of calculations that we as times face would have been absolutely daunting to earlier generations without the kind of technological infrastructure that you point towards. So it opens up a distinct set of calculations that we're willing to undertake because of the assistance that modern technology provides. So let's leave with one final question that one of the folks in the question and answer session asked. Is mathematics invented or is it discovered? Is it a language, as Steve described, that perhaps is a language of human invention, or is it something that's somehow more fundamentally out there? Any thoughts on that final question from anybody? Jim, you want to start us off?
Yes. In 2018, I was on a panel discussion in New York City on this very question. And so the thing that I told people is, since I am a physicist and I do devoutly believe in quantum mechanics, my answer is it's both. That it is very much like quantum mechanics, that as you struggle to solve a mathematical problem, it feels like you're building a structure piece by piece by piece. But once you have the solution, it feels as if it was waiting for you to discover it. So as my personal experience is that it is both. It's both created and it was in some sense pre-existing. I don't know how to get away from that emotional response.
So Steve, you used the language in describing mathematics a moment before. Is that your view, that it is a language of human invention?
Yeah, but it's not only human invention. I think we've been beaten into it by thousands of years of thinking about nature. And many of the things we thought about nature simply didn't work, led to wrong ideas, false predictions, and so on. Gradually, we've interacting with nature, asking questions, we've learned the kind of questions to ask and the language in which to ask them. And that language is mathematics. And so perhaps mathematics is the way it is because it mirrors something in nature, even though it took human beings to create it in its present form. This question, I think, is above my pay grade.
I think that was a good answer. It absolutely earned your pay, without a doubt. Any final thoughts on any of the discussion today from the Nobel panel or from the discussants before I turn it over to final remarks? And yes, Bill, please.
So I want to leave everyone with a question to which I don't really expect an answer, but I think it's worth thinking about. A lot of us have talked about the possibility that there is a better understanding that we're working toward, that quantum mechanics may be an approximation to some better theory, as Steve suggested, that there are things yet to be discovered about the way the universe works. What I'm wondering is it possible that such a thing exists, that is such an understanding of the universe exists, but we as human beings simply don't have the hardware or the wetware that is sufficient to understand those things? The way people often say this is, well, dogs and cats are pretty smart. They can learn to do all kinds of stuff, but they cannot learn quantum mechanics. And we don't think that any way that we might devise to teach dogs and cats quantum mechanics is going to be successful. So maybe we're simply not sufficiently built to understand the theory that actually is going to supersede quantum mechanics, or the theory that supersedes that. And I certainly don't know the answer to that. I wonder whether we might get better hardware by adding silicon to our wetware, or some other kinds of accoutrements. But I think it's something that's interesting to speculate about.
It's absolutely an interesting thought. And I just would leave you with the one thought that my dog Scarlet, who's a mix between a lab and a golden retriever pit bull, she has calculated the eigenvalues for the particle in a box. So just, I think we don't always give dogs the credit that they're due. Anyway, with that facetious remark, I will now pass it back to the organizers, who I believe want to make one final remark to wrap up today's program.
I would be delighted just to make the briefest of remarks. So I'm Carol Suter, I'm the Master at St. Cross College, which hosts the Centre for the History and Philosophy of Physics. We've run events for a number of years now, but we have never been able to bring together such an extraordinary evening, in the UK at least, and such a wonderful panel. I can't imagine that it will be done again very easily. So can I just offer an enormous thank you to all of our panelists, to our discussants, to Dr. Joe Ashbourne, who's the director of the centre and who had the completely crazy idea of putting this together and has managed to bring it off. And also to the hundreds and hundreds and hundreds of people across the world who tuned in to hear some genuinely mind-expanding presentations and discussions today. We are extremely proud of our association with the centre, and I could not be prouder of being involved with this sort of event. I don't want to keep anyone any longer, so may I just say thank you very much indeed to everybody who's been involved in this. Thank you.